formulas, and I know that's probably getting some of you worried because it's like, what do we have to memorize here? You don't. You have to memorize the Pythagorean identities. We expect you to know those. We expect you to know the cofunctions, where you had, theta, pi over 2 minus theta. You have to know those, which ones are cofunctions. And then we expect you to know the even or odd. The rest of this, if you need it, it'll be given to you. So, do you need to know the formulas? You need to be familiar with them so that when you see it on the test, you go, oh yeah, that's right. When you see this one and it says prove the reduction formulas, hopefully you'll go to the left-hand side right away. And you'll say to yourself, that's sine. Now, it's not too hard to memorize these anyway. And that's because sine will always go sine, cosine, cosine, sine. And then you put these two in for each one of those. So it'll be sine of x, cosine of pi, cosine of x, sine of pi. And then with sine, you get to keep whatever sign there is between these two. So this one will be a plus. And then you realize, wait a minute, cosine of pi. If I go out to pi, I have it backwards. That'll be negative 1, 0 out here. So my cosine of pi is negative 1. So this will be sine of x times negative 1. And my sine is 0. So the second piece of this is going to be totally gone. And if you multiply the sine of x times negative 1, you get negative sine of x. And that's the proof. That's it. Like it says, prove the reduction formulas. This one down here, very similar. It says if you do the cosine of x plus 3 pi over 2, you're supposed to get sine of x. With cosine, it's always cosine, cosine, sine, sine. But because the order stays the same, this one has the opposite sign of whatever you see in the parentheses. So this one will have subtraction in there. But then you just go through and say, okay, I'm going to put an x here, a 3 pi over 2 here, and an x here, and a 3 pi over 2 here. And think visually about that 3 pi over 2 location. And realize that wherever cosine of 3 pi over 2 is, that's a 0. And back here, sine of x times the sine of 3 pi over 2, that would be a negative 1. This is gone. Minus a negative, when you multiply those together, is sine of x. So it's a proof because it says proving reduction formulas. But it's a proof that uses some algebra along with it because there are some of these that we can find. And that's the point they were making up in that paragraph above where it says, because we know special things about cosine and sine and any of those quadrantal angles, we actually can say, hey, it doesn't matter what they give us in here, plus 3 pi over 2, it's just going to be the sine of x, whatever that is. So it shortens it up a little bit. But we're probably not going to deal with this particular formula enough that we're going to feel comfortable just dropping down to sine of x. We would probably put it through the whole formula and then say, oh yeah, now I realize that this could have been done a little bit easier. So I didn't realize that we had everything but this on that day. So this is the only new stuff we're going to cover today, and that's tangent. Technically, we wouldn't need tangent, right? Because what is tangent in terms of sine and cosine? Sine over cosine. So we could just use the formulas that we had before. In fact, a lot of us do that, and that's because the formulas for tangent sometimes get a little complicated. But if we're giving them to you, why not? So the tangent of u plus v equals the tangent of u plus the tangent of v, and I notice tangent, tangent, and a plus because the formula had a plus. But then in the bottom, I have 1 minus the tangent of u and tangent v. And then with this formula, I see the subtraction up above. So it's prominent. That sign is prominent in the top of that fraction, which is the numerator every time. And And then you just use the opposite sign on the bottom. So it's not hard to memorize these formulas either, but you don't have to. You don't have to. So this says we're going to prove a tangent reduction formula again. But we want to start with our nice new formula up here. So I see that this one says tangent of theta minus 3 pi over 2, and that's this formula. So we'll have the tangent of theta minus 3 pi over 2, because first off, it always drives me nuts the way the book does fractions horizontally, so I like to see them separated. And we'll break that apart using the formula. So it says start with tangent of u, okay, that'll be tangent of theta, minus tangent of v, tangent of 3 pi over 2, over 1 minus tangent of theta times tangent of 3 pi over 2. Oh, thank you. So now, next up would be, what's the tangent of 3 pi over 2? That's the next thing we would need to know. You remember the coordinate trig for tangent? Tangent is always y over x. So if we take a look at that 0 and negative 1, we want to know what we're going to get for the tangent. That's not going to be something we can do, right? Okay. Here's why. When you're proving a quadrantal angle reduction formula, you can't use the formulas that you have at that point. You have to back up. So when I was talking earlier about how sometimes it's easier to just go ahead and use sine and cosine, this is one of the reasons right here. So what we're going to do instead is we're going to do the sine of theta minus 3 pi over 2. And you might encounter that in the homework too, where you're starting to do one and you realize, wait a minute, this isn't going to happen. So we'll take a step back and we'll say, okay, tangent's not going to work with this because our tangent would be undefined. But we can use sine and cosine. Do you remember the pattern? If you're doing sine, what's the pattern for theta minus 3 pi over 2? Sine, cosine, cosine, sine. Do you get to keep the sign or do you have to change it? Keep it. And then we need a theta. And we need 3 pi over 2. How about for cosine? Cosine, cosine, sine, sine. Do you get to keep the sign or do you have to change it? Cosine changes. And then we just put our theta and our 3 pi over 2 on there. Now, ask yourself, is this something we're going to be able to do? We couldn't do tangent because our tangent was undefined. Are we going to be able to find a cosine for 3 pi over 2? Are we going to be able to find a sine for 3 pi over 2? So that's what we need to do. So let's take a peek here. We're going to have sine of theta. What is the cosine of 3 pi over 2? Ooh, I like that one. Cosine of theta again. How about the sine of 3 pi over 2? Negative 1. So on the bottom, cosine of theta, we already said cosine of 3 pi over 2, 0. Sine of theta, and then sine of 3 pi over 2 is negative 1. Now let's see what we have. Oh, thank you. I wrote it down over there, just didn't catch it here. All right, so on the top, what do we have? So what's that? Is that what we were supposed to get? I was just thinking earlier, I think there's one in your book, because I remember doing one in the homework where you go to do tangent and something's undefined. And then you think, okay, backup plan, what's my backup plan? Sine over cosine, and you'll get it that way. So there's our negative cotangent theta. Now, when we have actual radians that we have to find, that takes a little more thinking. So I'm looking at this and thinking, it says use a sum or difference formula. That means I need two angles that are somehow going to give me 5 pi over 12. There is something that I know good stuff about. That means it's a 30, it's a 60, or it's a 45, because we know all that information. So, start thinking. And I had you do this on the notes from when I was gone. In terms of the 30, 60, and 45. Let me try a drink here. Our denominators 4 for the 45 degree. For the 30 degree, it's a 6. And then for the 60 degree, it's a 3. So our least common denominator for those numbers would be 12. So we want to think in terms of 12ths, and if we have pi over 12, that'd be the smallest one. And then 2 pi over 12, because that represents pi over 6, that's going to be a useful angle. That's 30 degrees, we know that one. And then if we have 3 pi over 12, that will give us pi over 4, which again, we know stuff about that. That's 45 degrees. 4 pi over 12, and that's going to be pi over 3. And we would do as many of these as we needed to do until we found some combination that would work really nice for 5 pi over 12. You see two of them up there that are going to help us out with 5 pi over 12. Those two right there. 2 pi over 12 plus 3 pi over 12 is 5 pi over 12. 5 pi over 12 is not an angle that we know anything special about. We wouldn't be able to give them an exact value with that. But if we change this to the tangent of pi over 6 plus pi over 4, yeah, we can do that. So we'll use our new tangent formula, and that's at the top of your page there. So if we have the tangent of plus, on the top it's going to be tangent of u, which in this case will be pi over 6, plus tangent of pi over 4 over, how does the bottom of all this tangent formula start? 1. Used addition on the top, so what have we used on here? Okay. Now whether or not you memorize from unit circle or you use your special right triangles, either way you can get those values that you need. So, the first thing I'm thinking here is tangent of 5 pi over 12. Julie?
Does it matter the order it goes in? The pi over 6 and pi over 4?
It doesn't. No, and that's because addition is commutative and so is multiplication. So it's not a difference. Now, 5 pi over 12 is in first quadrant. Everybody see that? We're not going to go even halfway. So I'm not worried about signs, which means I can just use these two sketches. I don't have to make sure that it's in the right quadrant. And I can find my tangent for pi over 6. Pi over 6 is what in degrees again? 30 degrees. So we need opposite over adjacent. Well, 1 over the square root of 3, we know would be the square root of 3 over 3. Tangent of pi over 4 Any angle we go to here, opposite over adjacent, is gonna be a 1. And on the bottom, we're just gonna rewrite those. So it'll look like that. So now, that's really ugly. We obviously can't leave it that way. So what we have to do is figure out how can we at least get this to be 1 fraction over 1 fraction. And to do that, we'd think, well, the common denominator here is 3, so I'm going to multiply this 1 by 3 over 3. That'll give me the square root of 3 plus 3 over 3. At least I have 1 fraction on the top now. It's looking a little better. Oh, I'll have to do the same thing on the bottom. 3 over 3, except this will be 3 minus the square root of 3 over 3. And hopefully, you're already doing that multiply by the reciprocal in your head and seeing this comes out a little bit nicer. Not a lot, a little bit nicer. These will cancel. So now the question is, do we keep going? Well, why did we do this problem this way? Why didn't we just punch this into the calculator? Because the directions said find an exact value. And if they want an exact value, by golly, we're going to keep going. We're going to rationalize the denominator. This is supposed to be exact, so we want this to look nice. In order to get it to look nice, we're going to have to multiply the top and the bottom by the conjugate of the denominator. Remember that one? Conjugate. What's the conjugate for 3 minus square root of 3? 3 plus the square root of 3. So our real focus is on, hey, the denominator is not going to have a radical anymore. So let's go ahead and multiply first times first, which is 9. But outside times outside and inside times inside are going to cancel out. Last times last will be a negative square root of 3 squared, which is minus 3. So that did exactly what we wanted to do. We got 6. You might as well check that first to make sure, hey, there's not going to be any radical in the denominator. And then just take your time, because this is going to take a little bit longer, and do your square root of 3 plus 3 times 3 plus the square root of 3. In fact, I'd be really tempted to just turn these two around so that you can get a nice pattern there. But either way, 3 times the square root of 3 is 3 square roots of 3. Outside times outside plus 3. Inside times inside plus 9. And then last times last plus 3 square roots of 3. So we end up with 12 plus 6 square roots of 3, which we can divide by 6. You could think of it as factoring. And there's a really nice looking exact answer. A lot nicer than if we'd have left the square root of 3 plus 3 over 3 minus the square root of 3. So when they're exact, we go through all of what we know about radicals and rationalize the denominator. All right, that is it. And I certainly could come up with another one of these if you needed it. But 43210 means, how do you feel about using those formulas? Well, then I'll just give you some more time for a change, huh? So, no new assignment, still the same.